Greetings! Welcome back. Today we are going to be talking about percents. This is chapter 2.5 in your book, and we want to do a little bit of background before we dive into 7.6, which is solving some more interesting type problems with percent. So today what we're going to do is just talk about what a basic percent is and some drawings that can help us remember some benchmarks for percents, and then we're going to look at a couple of different ways to reason about percent problems. So the word percent literally means per 100. So that cent comes from the Latin for 100. So you can think of it as per 100 or for each 100. So for example, let's say we had a statement like 12% of California's budget goes toward higher education. So what is that 12% telling us? One way to think about it is that California spends $12 per $100 on higher education. Or another way to think of it is for each $100 that California spends, 12 of those dollars go toward higher education, right? So 12%, 12 out of 100. And percents are actually really nice, especially for being able to compare different kinds of quantities. They kind of act like a common unit of measure in lots of ways. So again, back to the budget example. Suppose, just hypothetically, that in 1978, California spent $3.6 billion out of a budget of $20 billion on higher education, okay? And then by 2017, they spent $12.3 billion out of a budget of $105 billion. So just looking at those numbers, right, like, well, 12.3 billion is bigger than 3.6 billion. It's, it's quite a bit bigger. It's not quite 4 times as much. So by that metric, it might seem like California spends more on education. And in one sense, they do. But there's a lot of things that make those numbers not really good to compare. Like, for instance, in 1978, the dollar was not worth nearly as much in some way. So the value of the dollar has changed since then. So percents give us a way to kind of compare this spending money over these drastic different times. So if we want to compare them, let's look at them as percents and see what that tells us. Percents. All right. So what we do then is look at the 1978 numbers. So we're looking at 3.6 billion out of a total of 20 billion. And if we convert that to a percent, that means we kind of come up with an equivalent fraction that's out of 100. That works out to be about 18 out of 100, or 18%. Whereas the 2017 number, which was 12.3 out of 105, works out to be only about 12 out of 100, or 12%. So you can see that even though in raw dollars, it looks like we're spending more, if we look at the percentages, it shows us that California is spending quite a bit less on higher education than back in 1978. And these numbers are not exact, but they are actually kind of approximate from history. So that's what we're going to be looking at today, is percents, which are a shorthand way of writing fractions out of 100. And it's going to be nice for us to have some benchmarks to recognize. And so there are some pictures that can kind of help us orient ourselves to what we mean by something like 25%. 25 out of 100 is equivalent to 1/4. And so that's represented in the picture as 1/4 of that circle. So 50% is a half. And so what we've got is this rectangle that we've cut in half. So half of it is shaded, and that represents 50% of the rectangle. And similarly, we break this square up into 4 equal pieces. We shade in 3 of them. 3 out of 4 is 75%. So I just want to remind you that these are actually values that you probably want to have handy if you don't already. They're just going to make solving percent problems a lot easier and estimating percents a lot easier if you can kind of remember these fraction equivalents to common percents. So 25% is 1/4, 50% is a half, 75% is 3/4. And a couple others that are nice to know, 10% being 1 out of 10. So 10 is kind of hard to count all at once, kind of hard to subitize, right? Count by just looking at it. But if you see this grid is 2 by 5, maybe you can subitize 5. I don't know. That's kind of a tough one too. But a 2 by 5 grid is going to have 10, and one of those is shaded. And then similarly here we have 5. We've broken this rectangle up into 5 equal pieces, and exactly 1 is shaded. 20% is 1/5. And then finally, 5% is another good one to know. 5% is the same as 1 out of 20. So that is a 5 by 4 grid, which is how you can tell that there are 20 total rectangles, excuse me. And there's 5% of them are shaded, or 1 out of 20. Okay, so the last thing that we want to do is use these kinds of benchmarks to reason through some percent problems that we might come across. So I'm sure many of you have come across the problem where you want to calculate a tip based on a dinner bill. We're going to start with some basic simple numbers so that we can see how the reasoning works. And later on, we might look at some examples where the numbers don't work out quite so nice, maybe in another video. But let's say you and your friends go out and the dinner works out to be $50 and you want to leave a 15% tip. So one way you could do that, the book actually talks about this as reasoning through 1%. So you can think about $50 is 100% of the bill, right? And then oftentimes it's not too hard to calculate 1%. So just divide by 100 or break it up into, take 1/100th of the bill. And that in this case would be 50 cents. Now, I actually don't think 1% is a great benchmark to use in this problem because you still have to multiply that number by 15, which is not really very easy to do, especially not in your head. I think a better benchmark for this problem would be to do 10% instead of 1%. So 10% of 50, right? 1/10 is again not too difficult to calculate. $50 becomes 10% of that is $5. Okay, but that's not exactly what we need for the tip. So how do we get that? Well, one way to think about it is that what we need is another 5%. And 5%, doing 1/20th is not always easy to do in your head, maybe especially depending on the numbers. But in this case, since we already know what 10% is, we can cut that in half to get the 5% value. And if we put those two values together, we will get the 15%. And so adding those together gives us $7.50 as the 15% value of the total $50 bill. Okay, so that's called reasoning through benchmarks. Is we try to use our knowledge of multiplication to help us kind of zoom in on the percent that we actually want to calculate. So in this case, it was easier to use 10% as a benchmark and kind of work with that value to find what 15% was. Okay, so let's look at another example. In this example, we're going to try to calculate, instead of the percent value, what we're going to try to figure out is what the missing total is. So the Hispanic population at Chico State is approximately 6,000 students, which makes up about 30% of the total student body. So the question is, what is the total student population at Chico State based on these percentages, right? If 6,000 is 30%, then we're interested in trying to figure out what is 100%. And we can use benchmarks to do that again. So this time, though, what we'll start with is what we know, which is that 30% corresponds to 6,000. So again, we want to think of a useful benchmark that we could calculate without too much difficulty. And so I invite you to pause the video here and actually think about this. Like, what would be a useful benchmark out of 30% that we could use to figure out what 100% is? So for me personally, especially because the 6,000 is divisible by 3, is a multiple of 3, I'm going to use 10% again. So I can calculate 10% of the total because I'm just going to break that 30% up into 3 pieces, 3 equal pieces, right? And so if I take 6,000 and break it up into 3 equal pieces, I know they're each going to be 2,000 students. So that means if 30% is 6,000 students, then I can break that up into 3 equal pieces to figure out that 10% of the total student body is 2,000 students. And then from there, hopefully it's not too hard to get to 100 using 10%. So now we would take 10 times that, right? So if we take 10% times 10, that's going to give us 100%. So if we have 2,000 multiplied by 10, we find that the total student population is about 20,000. Again, these numbers are not 100% accurate. Shouldn't have used percent there, sorry. I did not mean that pun. But they're approximately what the ratio at Chico State actually is. Okay, so that's how we can reason through benchmarks. It can be a pretty powerful way to do at least nice numbers in your head with percentages. Another way that we can think about reasoning with percents is with equivalent fractions. And this one is kind of nice because it relates to what we talked about with ratios. As we can think of using the multiple batches perspective here a little bit, and I'll try to make that connection. So again, let's go back to the same dinner problem and see if we can solve this a different way. So our bill is $50. We want to leave a 15% tip. Well, now we're going to think of this as equivalent fractions. So remember that 15% means 15 out of 100. And so what we want to know is that question mark value, right? Like, what would be the amount of money that would be equivalent out of 50? What would that numerator need to be so that these fractions would be equivalent? And we can think of this kind of as a multiple batches, right? So here's how I see this. This 50 goes in to 100 twice. So you can kind of think of, we would need 2 batches of whatever that 50 part is to get 15 out of 100. So what would we need 2 of to make 15? Yeah, so we're going to do this is to keep these fractions equivalent, right? The number that we would need to double to get 15, or another way to think of it is half of 15, would be 7.5. So 7.5 out of 50 is the same as 15 out of 100. And that's another way of saying that 15% of 50 is 7.5. So equivalent fractions can be another way that we can use these, that we can solve these percent problems. Okay, so one more example. Let's look back again at the population ratio problem we were looking at. So again, about 6,000 Hispanic students at Chico State, which makes up about 30% of the student body, the total student body. So we're going to set up the fraction. So again, what I would like you to do, this one is a little different than the tip problem. I'd like you to pause the video and try to set up the equivalent fractions problem. And what we know is, we know 30% stands for a fraction, and then we want to find the missing total. So pause the video and take a few seconds to try to set up the equivalent fractions we're looking at. All right, so if you struggled with that, don't feel bad. This is a new skill, and we're going to be practicing it, and hopefully we'll get better real quick. But remember, 30% means 30 out of 100. And now in this case, the 6,000 is the 30%, right? So that's actually the numerator, and the unknown quantity here is the total, which corresponds to the 100%, so that is what goes in the bottom. So we don't know what that is, but again, we can kind of think of this in a multiple batches way, which is, how many batches of 30 would we need to have, right? So if 30 out of every 100 students at Chico State are Hispanic, how many batches of those would we need to have to make up the whole student body? So then we kind of are asking, how many times does 30 go into 6,000, or what would we need to multiply 30 by to get up to 6,000? How many batches do we need? And those numbers can be kind of big. I'm not going to pretend like this is a trivial calculation. The numbers work out nicely, but they're still big numbers that are kind of hard to reason with. But again, you can break the problem down a little bit. So we can think about, let's see, 30 times 100. Well, 30 times 10 would be 300, so that's not going to be quite enough. 30, so let's write that down. So 30 times 10 would be 300. That's not quite up to 6,000, so let's go up a little bit more. Let's say 30 times 100. Okay, that's just another 0, right? That's a factor of 10 more, so we have 3,000. And we're almost there. That's half. So maybe if we multiply by 200, we're going to get 6,000. So this number, you can kind of think of this, we need 200 batches, which is a lot of batches. But we're talking about the population of Chico State, which is pretty big, right? So then we would take 100, and we would multiply it by the same 200 batches to find out what the total would be. And just as before, 200 times 100 is going to be 20,000. Again, I'm not pretending that's a trivial calculation. Those are some big numbers, but we could always use a calculator to help us think about some of those big number calculations. But the point is that we can reason about percents using equivalent fractions. And we'll look into some more of this. Like I said, in chapter 7.6, we'll talk about how to solve some other kinds of percent problems using some of these same skills of benchmarks and equivalent fractions. All right, that's all we have for today. Catch you next time.